Welcome back, everyone. Today we're diving into a really fundamental battle in computer science. We're talking about order versus chaos in databases. As part of your software engineering program, it's absolutely vital to understand how a database manages millions of simultaneous requests without just collapsing into complete chaos. So in this explainer, we're unpacking Chapter 10. We'll explore exactly how database management systems, or DBMS for short, use things like transaction management and concurrency control to maintain perfect data integrity. Let's get into it.
Here's our roadmap for today's lecture. 1. Introduction to database transactions. 2. The ACID transaction properties. 3. Concurrency control and problems. 4. Schedulers, locks, and deadlocks. 5. ANSI isolation and database recovery. And finally, 6. Essential concepts and summary.
All right, let's kick things off with Section 1, Introduction to Database Transactions, the building blocks of data integrity.
So think about this. When just you interact with a database, it's pretty straightforward, right? But at a real-world scale where thousands of users are reading and writing data at the exact same time, we need a really rigorous system. And these interactions are built on what we call transactions. Before we go further, let's define that. A transaction is a logical unit of work composed of one or more SQL statements. And here's the kicker. It must be entirely completed or entirely aborted. There's absolutely no middle ground. No intermediate states are acceptable here. The database has to go from one consistent state to another consistent state.
Let's look at a classic example to see why this all-or-nothing behavior is so crucial. Imagine a simple bank transfer. Step 1 is to subtract $100 from account A. Step 2 is to add that $100 to account B. Now, what happens if the power goes out right after Step 1 but before Step 2? Well, if the database just accepted that half-finished intermediate state, account A would lose $100 and account B would never receive it. The money would literally vanish into thin air. And that is exactly why the entire unit of work must be rolled back or undone if it's interrupted. If every single step doesn't finish, the transaction is completely aborted.
And you know, this plays out constantly in much more complex scenarios. Take a look at this sale code database schema. A real-world transaction, like selling a product to a customer on credit, isn't just one simple step. You have to write a new customer invoice. You have to reduce the quantity on hand in the product table, update the actate_transaction table, and finally update the customer balance. All of these SQL statements must complete successfully together. We use a SQL statement called commit to save these changes permanently, or roll back to abort and undo the whole thing if any single step fails. So, just to recap our first section, transactions are logical units of work that take a database from one consistent state to another, and they must either complete fully or abort completely.
Moving on to Section 2, the ACID transaction properties, the universal laws of database stability.
Okay, pay really close attention here because this is a crucial exam concept. Every individual transaction must pass what we call the ACID test. These are basically the rules of engagement designed to prevent database chaos. The A stands for Atomicity. As the name implies, it means the transaction cannot be divided into smaller units. It's that all-or-nothing rule we just talked about. If a transaction has 4 SQL requests, all 4 requests must be successfully completed. If even one of them fails, the entire transaction is aborted and the database state remains completely unchanged.
The C stands for consistency. This means the transaction must take the database from one valid, consistent state to another. If any part of the transaction violates an existing business rule or data integrity constraint, say, for example, if an update would cause a customer's balance to exceed their credit limit, the entire transaction is aborted. It absolutely has to maintain the database's consistency. Next, the I stands for isolation, and this one is incredibly important in multi-user environments. Isolation means that the data used during the execution of a transaction cannot be used by a second transaction until the first one is totally finished. The data is temporarily locked away. This ensures that concurrent transactions don't interfere with each other and cause crazy calculation errors. Finally, the D stands for durability. Think of this as your ultimate safety net. Durability ensures that once a transaction is successfully completed and committed, those changes are permanent. Even if the server suffers a critical hardware failure or a power crash just 1 second later, those committed changes will not be lost. So to quickly recap the ACID properties, a transaction must be atomic, consistent, isolated, and durable to survive the real world. Let's jump into Section 3, Concurrency Control and Problems, the villains threatening our data. So a single user database automatically guarantees isolation, right? Because only one transaction happens at a time. But in a multi-user system, what happens when hundreds of concurrent transactions try to access the exact same data simultaneously? Well, this introduces real villains that threaten our data integrity. And to fight them, the DBMS uses concurrency control. Before we see the problems, let's define that. Concurrency control is a DBMS feature that coordinates the simultaneous execution of transactions while preserving data integrity. The main goal here is maintaining what we call serialization. Serialization just means that even though transactions are running concurrently at the exact same time, the final outcome must be exactly the same as if they had been executed sequentially, one right after the other. Now, let's look at this exact scenario to see what happens when concurrency control fails. Meet our first villain, known as a lost update. Imagine the database says, we currently have 35 units of a product in stock. Transaction 1 wants to purchase 100 units, so it reads the value 35. At the exact same millisecond, Transaction 2 wants to sell 30 units, and it also reads the value 35. Transaction 1 adds 100 to 35 and saves 135 to the database. But then, a microsecond later, Transaction 2 subtracts 30 from its initial read of 35 and saves 5 to the database. Transaction 1's update was completely overwritten and lost forever, all because the system didn't isolate the data.
Aside from lost updates, we face two other major problems. First is uncommitted data, which is also known as a dirty read. This happens when one transaction is allowed to read data that another transaction has modified but hasn't yet committed. If that first transaction ends up being rolled back, the second transaction has literally based its calculations on data that officially never existed. It's a huge mess. The other problem is inconsistent retrievals. This happens when a transaction is trying to calculate summary data, but while it's doing that, another transaction is actively updating that exact same data. You end up with a completely miscalculated total. So, a quick recap here. Our three main villains in a concurrent environment are lost updates, uncommitted data, and inconsistent retrievals.
All right, Section 4, Schedulers, Locks, and Deadlocks, the heroes of data integrity.
So how do we actually defeat these concurrency villains? Well, the primary hero inside the DBMS is a component called the scheduler. The scheduler establishes the exact order in which concurrent transaction operations are executed to ensure that serialization we talked about. And its primary weapons? Locks. A lock guarantees unique access to a data item. We generally use two types of locks. An exclusive lock is used when a transaction wants to write to the database. It completely locks everyone else out. No one else can read or write to that data until the lock is released. On the other hand, a shared lock is a bit more forgiving. It's used when a transaction only wants to read data. It allows other transactions to also place shared locks to read the same data, but it absolutely forbids anyone from placing an exclusive lock to write to it.
However, as great as locking is, it isn't perfect. It introduces a brand new problem called a deadlock. You'll sometimes hear this dramatically referred to as a deadly embrace. A deadlock is a condition where two or more transactions wait indefinitely for each other to release a lock. Imagine transaction 1 locks data X and is waiting for data Y. Meanwhile, transaction 2 has locked data Y and is waiting for data X. Neither can proceed. They will literally wait forever, like two incredibly stubborn people refusing to step aside in a narrow hallway. Because of this, the DBMS has to use special algorithms to detect these deadlocks, automatically abort one of the transactions, and release the locks so the other one can finish. To recap this section, the scheduler is our hero, using exclusive and shared locks to keep order, but it constantly has to watch out for those deadly deadlocks.
That brings us to Section 5, ANSI isolation and database recovery, standards and safeguards.
The industry actually standardizes how we apply these locks through 4 ANSI SQL isolation levels. Let's walk through them. Read uncommitted is the least restrictive. It basically doesn't place locks, meaning it's incredibly fast, but it allows those dangerous, dirty reads. It is a really common misconception among students that this level is safe to use for critical data. It is absolutely not. Don't make that mistake. Next is read committed, which is the default for most databases like Oracle and SQL Server. It ensures you only read committed data. Then, repeatable read goes further to ensure queries return consistent results by using shared locks. Finally, we have serializable. This is the most restrictive level. It guarantees perfect transaction isolation, but it comes at a massive cost to concurrent performance because transactions just have to wait in line a lot more.
But what happens if this system completely crashes, like a total power failure?
Our ultimate safeguard here is the database transaction log. As you can see, the DBMS keeps a meticulous, continuous record of every single operation, what the data was before and what it was changed to. By using a write-ahead protocol, this log is saved to disk before the actual database is updated, so if the server crashes, upon reboot, the DBMS reads this log. It will roll back any uncommitted transactions to their before values and roll forward any committed transactions that didn't quite make it to the physical disk, ensuring perfect durability. So in short, to recap, ANSI levels dictate how strict our locks are, and the transaction log ensures we can always recover from a crash.
Finally, Section 6, Essential Concepts and Summary, Securing Your Knowledge.
We have covered a lot of really deep theory today, so let's summarize and secure this knowledge for exam day. Here is what you absolutely must remember. First, a transaction is a logical unit of work that must be entirely completed or completely aborted. Second, you must know the ACID properties by heart: atomicity, consistency, isolation, and durability. Third, understand that concurrency control is what prevents those villains like the lost update and uncommitted data. And finally, remember that the DBMS relies on schedulers using exclusive and shared locks to maintain order and the transaction log to guarantee recovery after a failure.
I'm going to leave you with a final, provocative question. We know that strict locking and serializable isolation levels slow down performance by forcing transactions to wait. So as software engineers, how do we optimize our complex queries to ensure maximum performance without sacrificing our strict ACID guarantees? Think about that for a bit, because that is exactly what we will be covering in our next chapter on database performance tuning and query optimization. Thank you so much for tuning into this explainer, and I will see you in the next one.